Hello, welcome again. So, we will be continuing in this class the discussion about the structure and bonding of metallocene compounds. So, in the last class, if you remember, we discussed about the different type of ligands with pi system, and we discussed that the different modes of the cyclopentadienyl ligands, and today we will mainly discuss about the different type of the metal cyclopentadienyl complexes can exist, and then we will try to understand the bonding very simple way with the help of molecular orbital diagram, and we will try to understand the HOMO and LUMO, okay, and the electronic properties, okay, which will be helpful for our further discussion. Okay. So, as you know that that eta 5 Cp mode, okay, we discussed extensively in the last class that if you have, we will discuss the synthesis at the later after understanding the bonding, and then we will discuss how to synthesize, okay, the ligands as well as the metal complex, the common synthetic protocols. So, if we tell it is a Cp minus because it is synthesized from the CpH, okay, and if you put a base, okay, then you get the Cp minus with 6 electron donor, okay, and you will see that it, okay, makes a bond like this, and this is called the eta 5 mode, okay. And most common metallocene complexes are actually with this type, where you will see that we have a Cp bond here, and here we have Cp bond. So, two Cp ligands, okay, which are parallel to each other, okay, just a parallel to each other, fine, Cp and Cp. And if you just imagine a sandwich, okay, how the sandwich, two bread slice, and inside what we put stuffing. And if you remember, if you can just imagine that these are my breads, okay, and these are just stuffing, okay, or just put a tomato, then how does it look like? It will look like a sandwich compound, okay. So, this kind of compounds is called sandwich, organometallic sandwich compound, okay. Very interesting category of complexes, and you see the beauty of the structure, metal center and the Cp ligands which are bonded, okay, through the pi through the pi system of the two Cp ligands. And a very common example is the ferrocene. I will discuss, okay, in the next slides or so about the ferrocene, okay, the bonding and molecular orbitals. So, very common examples where the two Cp are parallel to each other, and generally most of the 3D transition metals, okay, 3D transition metals are generally form this kind of Cp2M complexes, okay, like iron 2 plus, nickel 2 plus, manganese 2 plus, cobalt 2 plus, vanadium 2 plus, okay, generally form this kind of cyclopentadienyl complexes where two Cp ligands are parallel to each other, okay. This is also quite common, where you will see that here 2 Cp and here 1 Cp ligands, okay, just 1 Cp ligands, okay. So, this is called half sandwich complex. That means you see somebody is, if you just imagine that upper blade slice has been eaten away by somebody in a sandwich, okay, then what will left over? You will be a sandwich, okay, where the upper slice bread is missing. So, this kind of scenario, it is called the half sandwich complexes. This is also called as a piano stool. Okay. Why it is? Because you just try to imagine. So looks, this is like your, if you just this one, okay, and you make, okay, so this is your leg of the piano stool. Okay, so this would be the like a leg. So it is sometimes lovingly called piano stool Metallocene complexes. Okay, so there see the structural different structural variation here. Actually, if you see that how it can form, so suppose say for iron, so iron 2 plus is a D6 system. Okay, so if I check it, validate by 18 electron, so this is 6 electrons from the metal, and the Cp minus, okay, it exists as a anionic Cp, so Cp minus is 6 electron again, so 6 plus 6, 12, so it is 18 electron. Okay, so this is 18 electron complex. Okay, now if I replace one Cp by 3 ligands with 2 electron donor, then again it will be 18 electron system. So you can make, so compounds should be stable. Okay, if with the same oxidation state. Okay, so if you are satisfying the 18 electron by replacing the Cp ligands and with the proper oxidation state of the metal center. Not only that, there are other type of ligands. Here you will see that is, this is the Cp3m type. Okay, this is the Cp2mlx. That means again you will see that here all the 3 Cp ligands, there is no other monodentate or bidentate ligands. Here you see that in this case one Cp ligand has been replaced by the 3 ligands. So this is a generic structure I am giving. Okay, we will discuss the specific example later. So here 3 Cp ligands, here 2 Cp ligands, here 2 Cp ligands, but other non-Cp ligands are there. This may be 3, this may be 2. Okay, so depending on the oxidation state of the metal centers, these ligands will vary. Okay, 3L or 2L. Okay, and here you will see that one Cp ligands and the other ligands monodentate. It may be monodentate, it may be chelating, it may be bidentate. So this is a very code structure I am trying to show to give a flavor that what kind of structural variations is possible in the metal cyclopentadienyl ligands. Okay, another possibilities, okay, for the bend. So this is, you will see that this one is parallel. Okay, but here the beauty is that this is not parallel. Here these 2 Cp ligands are not parallel. Okay, so this is basically in the ferrocene, like the B category, it's are like that one. Okay, and in the C category, so this is like this one. Okay, like this one. So it is bent, not parallel. Okay, and actually we are in this course, we are more interested about this bent cyclopentadienyl complex. But to understand the bonding, we should first start with the parallel Cp2m complex, that is ferrocene type of complex. Okay, then we will try to understand the bonding and reactivities with the bent Metallocene compounds. So the catalyst we are interested to learn and to understand the reactivity and the mechanism is basically based on the bent Metallocene compounds. And group 4, okay, the group 4 metals, as example zirconium and titanium. Okay, these kind of metals are formed this bent kind of structures. Okay. So, not only that, 3D transition metals also can form the bent Metallocene compounds with some, if you do some engineering on the Metallocenes. As example, I will show one engineering of the Metallocene where you can see that this is bent. Okay. So, in this category I will show here. So, this is CP and you see these are bent. Okay. And when it will be bent, if you put some bridging here, as example like this one. So, here you will see this is called the fen type of Metallocene. Okay. Metallocenophen, this is called Metallocenophen, and you see that this what we are doing, we are basically threading the two CP rings by a one bridging atom. This may be silicon, carbon, okay, or multiple atoms. Okay, so we have to design in such a way that these two CP rings are threaded, and then you will see that these CP rings will be bent, and the bent is obvious because this has been threaded now. So, there is a strain in these molecules. Okay. So, this would be strain molecules, and this is very useful monomer for making a different type of polymers, that is the organometallic ferrocene containing polymer. So, what I am trying to tell that there is a lot of structural variation in the metal cyclopentadienyl complexes, whether you see that the two CP positions are in a different position, two CP ligands are in a different position, whether it is a parallel, whether it is a bent, whether it is the two CP rings are threaded to induce the bend or to induce the strain. And some cases you will see for this category, okay, these two CP rings, cyclopentadienyl rings, it not necessarily you have to thread it to induce the bending. So, that is the its inherent structural properties. So, this is, I am sure you are very interested and excited that how this kind of structural variation happens. Okay. So, before that, let us start from a simple, okay, and well known Metallocene compounds, okay, to understand the bonding between the metal and CP. Okay. So, this is a ferrocene. Okay, as I told that this is the category of the B in this category. Okay, so where CP rings are parallel to each other. Okay, so here you will see that again is like a, as I explained, just it is like a sandwich type of structure. So, if you see this is two bread slice and iron is imagine as a stuffing. So, you will get the sandwich, that is why it is called sandwich type of complexes, sandwich like structure. And why the name is Metallocene? Is basically these are aromatic in nature, okay, this CP minus. So, that is why it just, if you take the like a benzene, from the benzene the scene has come, and metallo come from the metals, transition metals. That is why the name is, the category of the name is Metallocene. Okay, like a benzene like similarity, benzene like structure, similarity in benzene. Actually, yes, there is a lot of similarities, okay, with benzene, particularly in view of the electrophilic substitution reactions. Okay, so whatever the benzene can show the reactivities, electrophilic, particularly electrophilic substitution reactions, the ferrocene also undergo the similar reactions, and many cases the reactivities is more than the benzene. Okay, so there are a lot of similarities between benzene and the ferrocene. Okay, I will discuss when I will discuss some general reactivity and properties of the ferrocene. and obviously, as I showed, this is it can follow the 18 electron rules. So if you the 6 electrons, this is 6 electrons, and this is oxidation state is 2. Okay, so iron 2 plus, because this is Cp minus, this is Cp minus anionic ligands. Okay, and the hapticity is 5. So this is eta 5, this is eta 5. Okay, so the hapticity is 5. Can you tell the what is the coordination number of iron here in the ferrocene? Okay, any idea? Okay, coordination number. So coordination number is, what will be the coordination number? Coordination number will be 6. Okay, because 6 electron pairs are donated to the iron. Okay, formally. So that's why coordination number 6, iron in oxidation state, plus 2 oxidation state, Cp minus ligands or monoanionic cyclic ligands. And you see, now if you see very carefully in this ferrocene, that ferrocene can also exist in 2 forms. Okay, here try to understand what is the difference here, that these 2 Cp rings are in a staggered conformation. Okay, so this is staggered conformation, and here you will see these Cp rings is in eclipsed conformation. Okay, and this is the difference between the staggered and eclipsed is around 4 kilojoule per mole. In solid state, actually the 2 Cp rings are exist as in just 9 degree away from each other. Okay, just 9 degree away generally. So that means these 2 Cp rings are slightly, okay, slipped from the eclipse position, 9 degree away. So and you know the point group. So if it for the eclipsed, this is D5H, and for the staggered D5D. So this can be taken as a homework. Find out the point group and assign the point group and show the symmetry, how you reach to the D5H and D5D point group by drawing the planes and the axis. Okay, and the ferrocene is very interesting. You see that you can this is commercially available, but you can synthesize very easily in your lab. We'll show the later that what are the synthetic procedures. It looks like very nice orange crystals. You can crystallize, you can sublime. Okay, routinely used for many purposes. Okay, many even the ferrocene based chiral ligands. There is a lot of chiral ligands based on ferrocene. Okay, ugizamine, josephos. Okay, there are lots. Okay, so these are very interesting and famous Metallocene compounds which has been discovered first in 1951. Okay, and then later it was characterized. Okay, and you remember that the Nobel Prize was awarded in 1973 to Wilkinson for the discovery of the structure or proposing the structure of this kind of Metallocene compounds. Okay, so we'll go in little bit more detail about the bonding. If you see that the ferrocene is like that. Okay, so you may draw, okay, on pen and paper with me, so that you understand much better. So very interesting. This actually compound was discovered accidentally. Okay, not the it was not targeted that this will be synthesized. And back in 18 back in 1951, okay, the two scientists called Kelly and Paushan, they actually tried to synthesize, okay, the fulvalin compounds with the reagent CpMgBr, okay, through the oxidative coupling in the presence of Lewis acid, okay, FeCl3. So what was their target? Their target was to make the okay. So their initial target was to make the fulvalin, okay, through the oxidative coupling of the CpMgBr, and they didn't get, they got a compound, okay, where the composition was matching with, okay, iron and Cp2, and it was very difficult that time to understand, because the model to explain the pi complex, metal pi complex, was not that time, it was very well known. So they thought that with this composition, so there may be possibilities of this type of complex, where they proposed that probably, okay, so here this is hydrogen and this is minus, so Cp minus, and so they proposed the ionic so it was proposed that probably this kind of, okay, ionic model, with the help of ionic model, that this kind of complex has been formed, or this kind of with the covalent, same composition but the covalent bond model, okay. So because that time iron carbon bond, okay, sigma type of bond was easy to understand, okay. So if it is, there is a sigma donor, alkyl or aryl based, then it can form the sigma bond, okay. So this is a traditional way, but however it was kind of a puzzle, because you know that 3D transition metal carbon bond, okay, with 3D transition metals was not kinetically, is not kinetically inert, okay, is very labile, and that's why it is very difficult to make compounds with metal carbon bond where metals is the 3D transition metals. 3D transition metals means like nickel, iron, okay, manganese, okay, like that. Although they are a report, but you have to do some special design, you have to design your metal complex with specific geometry, the specific ancillary ligands with particular oxidation state. So this is not easy to stabilize the 3D metal carbon bond. So this is a new type of, okay, proposed as a new type of, okay, organo iron compound was proposed, and it was in around 1963, after almost 10 years, the Wilkinson proposed the real structure. Wilkinson Fisher proposed the real structure that it is a sandwich type of model. So this is the model, okay, sandwich complex. And in 1973, okay, he got the Nobel Prize in discovery of the Metallocene structure. Okay, so 1973. So you see that there is a kind of a renaissance in organometallic chemistry. A new era developed where a different type of ligands, that is the pi electrons ligands, was came into picture, and it was a great interest to the scientists to discover with the discovery of this kind of a very unusual organometallic compounds. Okay, so you will see that there is a, after that there are lot of this kind of cyclopentadienyl and the allied cyclic pi complexes, the complexes with cyclic pi ligands were developed. As example, here I show this, you can see here, this is the very common, that is the ferrocene. Okay, here the CP rings, here you see this is the chromosine, here you see that these are the benzene here. Okay, so these are the benzene. So this is the C5 cyclic ligands, this is the C6 cyclic ligands. Here you see that this is the C5, and here 1, 2, 3, 4, 5, 6, 7. Here you see C7 cyclic ligands. So here you see 1, 2, 3, 4, 5, 6, 7, 8. So this is the C8 cyclic ligands. Okay, and here you see not only the homoleptic, there are other mixed kind of cyclic pi bonded systems were also reported. Here it is C5, here it is C6, here you see very interesting C4, here it is C5. So varying the, you can tell that versatility in Metallocene, varying the cyclic pi ligands. Okay, and obviously if you once you vary the cyclic pi ligands, you have to also vary the metal centers, the oxidation state, etc., to stabilize the particular Metallocene compound. So you see that there are the versatile complexes, okay, and versatile kind of metal centers, the CP ligands. Okay, and also there is some representative example, there are lots, because these kind of complexes are really very interesting, not only for academic purpose, also for various practical use. Okay, so now we will discuss about the molecular orbitals in pi system. This will help us to understand the bonding of between the metal center and the CP ligands. Okay, so let's start from a small, and then we'll apply to the bigger system. Okay, so let's assume that there is the pi orbitals of the ligands where only the C3, the 3 carbon atoms are there. Okay, or 4 carbon atoms are there. Now then we will try to understand the molecular orbitals, the pi orbitals of the pi ligand system, and then we will then try to find out the matching orbitals of the transition metals, and then we will try to understand the bonding between the metal orbitals and the pi orbitals of the ligands. Okay, so let's understand the molecular orbitals of the pi system. So here you will see that the pi orbitals here, one always when you will construct the molecular orbitals of involving only the pi system, at the lowest, what you will get? You will get the single orbitals at lowest energy. Okay, so that is the this part. Okay, this one. Okay, so single orbitals at lowest energy. Okay, fine. Okay, now next what will be there? You will be doubly degenerate okay set of orbitals, okay, slightly higher in energy, okay, higher in energy, fine. And then next will be again one set of doubly degenerate set of orbitals. Here orbital means all pi orbitals I am telling. So again higher in energy compared to this one. Okay. Now there is another properties. So here you will see that this one will be nodeless. Okay, and for the next set of degenerate orbitals which slightly higher in energy, that will have a one nodal plane. Okay, one nodal plane. Okay, and that is the with the containing the along the principal axis, and this one, that is the next degenerate orbitals, you will get the two nodal plane. Okay, so in higher in the second set of degenerate orbitals, you will have a one nodal plane, and then next degenerate set of orbitals with more higher energy, you will get two nodal plane. Okay, now in this way, okay, you will construct the further pi orbitals, molecular orbitals, and up to and you have to continue till the number of molecular orbitals are equal to the number of p orbitals involving in the pi system. Okay, so you need to continue like that. Number of molecular orbitals should be equal to the number of atomic p orbitals involving in the pi system of the ligand. As example, here you will see for C5, okay, you have one single orbitals at lowest energy. Now then you will see the two, that is the one set of doubly degenerate, one set of doubly degenerate. Now total you see that 1, 2, 3, 4, 5, because the 5 p orbitals, if you see, okay, so here this you draw the 5 p orbitals, okay, and these are conjugated. So you see plus 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 plus. So that means here you see the number of atomic orbitals is 5. So number of molecular orbitals of the pi system will also be total 5. So that means number of atomic orbitals or number of carbon atoms involved in the pi bonding. Okay. So here you see, and another one. So there may be the odd or even carbon atoms in the cyclic polyene system. So in this case, you have to consider one more point, that for odd carbon atoms, okay, the highest antibonding orbitals, that is the with in this case, like for Cp, the highest antibonding orbitals will be doubly degenerate, and when it is even, okay, even cyclic polyene system, then what will happen? You will see that we will have a singlet, okay, highest molecular orbital is non-degenerate, okay, like in this case you will see that is the degenerate, the highest one, okay, here, and for even carbon atoms this is non-degenerate, okay, here you will see. So non-degenerate, and this is for the, this I am telling for the highest energy, okay, highest antibonding orbital I am telling. This is very simple approach, but very effective, okay, fine. Now you have to understand here that if you view from here, okay, so you are viewing from here, so your eye, okay, is from here, so you are viewing from the viewing from the, so suppose you have a ferrocene, so I am just drawing the ferrocene structure, then it will be more clear. So like this one, okay, so if you view from the ligand, metal ligand, so from here you are viewing, okay, so we will try to understand the symmetry of the associated orbitals by viewing from the top, okay, towards the top down, okay, view. So here you will see we can assign, okay, the, or we can categorize the different orbitals, okay, of this molecular orbitals of the pi system as cylindricals, okay, as if the symmetry is cylindrical, then we assign as sigma, we assign as pi, one nodal plane, and we can assign as delta where you have a two nodal plane, okay. So what I am telling, that this will be, the symmetry will be sigma, this will be pi, and this will be, okay, delta, okay, as viewed from the top down, okay. So this is important, sigma, this is pi, and this is delta. So you will have a like for Cp, okay, our discussion will be mainly on the Cp ligands. So you will see here, so one sigma symmetry with single of the lowest energy, and then doubly degenerate will have a pi symmetry, and the highest energy, that is this one, will have a delta symmetry. So this is the sigma, this is the pi, and this is the delta, okay, and this will be this will be useful, okay, to understand the ligand group orbitals when we will consider two Cp orbitals. So you know that for ferrocene, okay, again I am drawing here. So here we have one metal center and two Cp ligands, okay, and you know the concept of the concept of the LGO, that is the ligand group orbitals. So once we know the molecular orbitals in the cyclic pi system, okay, like Cp, Now you have to consider the ligand group orbitals when there is a multiple CP ligands in the specific organometallic compounds. This LGO can form by addition and subtraction of the particular symmetry of the pi orbitals. So what we will see here, so here again I am showing that these are the sigma, these are the pi, and these are the delta. You will see there is no node, okay, if you see from the top, okay, and here you will see there are two nodes here, okay. So if you see this one, okay, like this one, okay, so there is no node, okay. So this is the sigma, and here you will see in this scenario, okay, you will have a nodal plane here, okay, or here. So two possibilities. So this is the pi, and another case, that is the highest doubly degenerate, you have a delta symmetry, okay, sigma, pi and delta, okay. So you have a no node, single node and two nodes. So similarly here, this is a simple way to present that is the three set of the pi orbitals associated present in the cyclopentadienyl ligand. Now what we will do, we will have to do the LGO, okay, and to construct the orbitals which can interact with the specific d orbitals of the metal centers. So what we will do, the addition and subtraction, okay, of orbitals, okay, fine, to form LGO, fine. Now then what we will do, okay, to construct the molecular orbitals in present in metal CP bond. So what we will do, we will try to combine the LGO, the specific LGO, with matching, here basically matching in view of the symmetry of metal orbitals, okay, to construct the molecular orbitals of the ferrocene or metallocene in general. So that is the way, okay, we will form the molecular orbitals of metal CP2 complex. That is our target, okay. So as example, like here you will see that I will give one example like this one, okay. So if I do addition, okay, and if I do the subtraction, so what you will get? You will get the A1G set of orbitals, okay, and if you do the subtraction, you will get the ATU set of LGO. So this is the LGO, this is also LGO, okay, with two CP rings, okay. Undergoing the ligand group orbital, you will get two LGOs, one is the A1G symmetry and one is the A2E symmetry, and you will see from the A1G is perfectly matching with the S orbitals of transition metals, okay. For 3D transition metals, that S orbital will be the 4s, and this one will perfectly match with the p orbitals, okay, of the metal centers, and for 3D transition metals this will be the 4p, okay. So perfectly matching the addition, the LGO by resulting from the addition of this set of pi orbitals of the Cp. By addition, we will get the perfect matching with the s orbital of the metal, and if you do subtraction, you will get the perfect matching with the p orbitals of the metal center. In this way, we can get the, you will see that here, okay, this is the A1G, this is the E1, okay, this is E1 star from here. So you will get the LGO orbitals, which now we have to match with the d orbitals, the metal orbitals d or s, 3d, 4s, 4p. So you know that if you take the 3d transition metals, the 3d, 4s and 4p these orbitals can interact with the LGOs resulted from the two Cp rings. Okay, and this is the way you can now form the molecular orbitals. Okay, here you see that these are the iron. Okay, if you consider the ferrocene, okay, and so these are the iron d orbitals. So these are the d orbitals, these are the s orbitals, and these are the p orbitals. Okay, so in the next class we will discuss some of the unique electronic properties of the molecular orbitals of the Metallocene compounds for the Cp2m category, with the specific example of the ferrocene, and then we will try to understand what is the unique electronic factors in the molecular orbitals of the Metallocene or ferrocene like compounds, and this will be very helpful to try to understand the reactivities of the Metallocene compounds. So in conclusion, we have understood now the type of cyclic pi ligands. Okay, now we understood the structural versatility in Metallocene compounds. Okay, and we understood the pi orbitals of the cyclic pi ligands. Okay, and then we constructed the LGO, and we understood that how this can or interact with the perfect symmetry with the metal orbitals of the perfect symmetry. So in the next class we will try to understand the molecular orbitals of these Metallocene kind of compounds, and these are the books you can read whatever we have discussed in the last two classes. So thank you, and we will discuss again, we will continue the discussion again in the next class. Thank you very much. See you in the next class.